Hello, everyone. In this video, we're going to look at the preliminary example in section 3.4 on applied optimization. So in section 3.3, the one we were just looking at, we saw how important global optimization is, meaning finding a global or absolute maximum or minimum. And we see that this is important because there are a lot of situations in which we want to find an optimal or maximum or minimum value. For example, we might want to optimize profits, minimize expenditures, optimize fuel efficiency. There are a lot of situations, and maybe you can think of some yourself. So in this section, we are going to be looking at some specific examples of applying optimization. Many of the contexts you'll see in this section include optimizing a geometric space, meaning optimizing maybe for area or perimeter. We'll also see some problems about optimizing cost to produce certain materials, like produce a can. And we will see a few algebraic optimization problems using graphs and functions. All right, so let's get into it with this preliminary example. So in this example, we are told that we have a farmer who has 2,400 or 2,400 feet of fencing and wants to fence off a rectangular field that borders on a straight river. She needs no fence along the river. We want to find the dimensions of the field that has the largest area. So in this situation, we want to optimize or find the maximum area. Okay, so in all of these problems, always the first step is to draw a picture. We want to draw a picture of the situation to really get a sense of what's going on with our problem. So what should the picture be? Well, we want to draw a rectangular field that borders a straight river. So let's draw that picture. Okay, so here's my rectangular field then. Okay, there it is, and it borders a river. So we're going to put river here. So then I'm drawing what should be the border of the field using the fencing we need. So what other information do we have? Well, we have that in total, she has 2,400 feet of fencing. So that means if we were to measure all along the fence, we should come out to a total of 2,400. Okay, so now the next step when we're doing these applied optimization problems is to identify what is given and what we need to find. To do that, what we need to do is label our picture. So I'm even going to add that as a second step. Label picture. So how should I label it? Well, I know I have the river here, but in order to get our hands on this field, I want to label this field with some dimensions. So I could call this length here X and this length here Y. And so now we need to identify what we know. So what do we know? Well, we know this information about 2,400 feet of fencing. So we know we have 2,400 feet of fencing. So we know that that needs to be equal to the perimeter of our field. So how would we compute the perimeter of our fields? Well, we just go around and adding up the dimension or the length of each side. So for us, that would look like X plus Y plus X, which is just 2X plus Y. So we know that. So now step 4 is to identify what we need to find. What we need to find. So we want to find the maximum area. Okay, well, how do we write area of this field? Well, area is equal to X times Y. Okay, so we have a really good setup so far. We've drawn the picture, we've identified what we know, what is given, and we've identified what we want to optimize area. So now what we need to do is to apply or use what is given to try to find the solution, which is the optimal area. Okay, so to do that, we need to, maybe I'll just continue writing steps here. We need to use the given to find max area. So notice that if we were just to maximize the area without this constraint of 2,400 feet, then we could just go as big as we wanted in this fence, right? But we have this constraint here. So we need to use that constraint in our area function. So here's use given to find area. And maybe instead of given, we could say constraint, because we're constrained to a certain amount of fencing. So let's just combine those together. So I have the 2,400 equals 2x plus y, and I have a equals x times y. So if I want to find a maximum of area, then I can't have two variables in my function. Right now, area is a function of x and y. So notice this constraint or this given gives us a relationship between x and y. So from here, I can solve for x or y. Let's solve for y to find area in terms of just x. All right, so let's go ahead and do that. So solving for y, I'm going to subtract 2x from both sides. So I'll get 2,400 minus 2x equals y. So now I'm going to plug this in for y in my area function. So doing that gives me area just as a function of x is equal to x times 2,400 minus 2x. And so now we've done the hardest part. So now we have a function for area in terms of just x. And so now we just need to find the maximum of the area function. So before we find that maximum, let's just summarize what we've done. So we've drawn the picture of the situation. We've labeled the picture with the relevant dimensions. Then we determined what we know or what is given, and that's the constraint here. And I'm going to write that down because in all of these problems, we're always given what is given is often a constraint. Then we determine what we need to find. We need to find maximum area. So we write a formula for the area. From there, we put the constraint into the formula that we are going to work with, or into that formula that we want to find something about. When we combine them, we get a formula or a function for the area just in terms of x. Okay, so now our next step is just to maximize that area function. So I have a new page for us. I'm going to rewrite that area function down here. A of x equals x times 2,400 minus 2x. Okay, so now we just need to find the maximum. And this we've seen before in the previous sections. So to find a maximum, we first need to find the critical values. So let's recall how to do that is we need to compute the derivative. So to compute the derivative, I'm going to take a step back and just rewrite an expanded form. So I don't have to use the product rule. I can just use powers. So if I multiply that x into each term, I get 2,400x minus 2x squared. Okay, so now we are set up to take the derivative. So the derivative just becomes 2400 minus 4x using the power rule. And so now to find the critical values, we set that derivative equal to 0. So I have 0 equals 2400 minus 4x. So solving for x, I add 4x to both sides. So I get 4x equals 2400. I divide both sides by 4. We can get out our calculator. Or maybe we can do that one in our head. 24 divided by 4 is 6. So 2400 divided by 4 is 600. So this tells us x is equal to 600. So x is equal to 600 is a critical value of our function. So to determine, so now we need to determine if area has a max at x equals 600. So to do that, so we find the critical values. Now we need to determine if the critical value is a maximum. To do that, we can create a sign chart. So this, if we recall, our vocabulary would be to use the first derivative test. So setting up that sign chart, I have my 600, that's my important critical value. So then I can use some test numbers. So I could use a number here like 100 and a number up here like 1000. And so now I'm going to test the derivative at those two values. So the derivative of 100, or the derivative of a at 100 would be that 2400 minus 4 times 100. And that we see is 2400 minus 400, which is very positive. So our derivative here is positive on the left. And then if we use 1000, our derivative at 1000 is 2400 minus 4 times 1000, which is 4000. So 2400 minus 4000 is definitely less than 0 or negative. Okay, so what does this mean then about what happens at 600? Well, if our derivative is positive on the left, that means we're increasing. Negative on the right, that means we're decreasing. So that means indeed 600 is a max. So let's go ahead and write that out. So what do we have? Since x equals 600 is the only critical value of a of x, and a is increasing on the left of 600 and decreasing on the right, again, of 600. This means the function a of x has a max at 600. And so if we wanted to draw a picture of what a looks like, so a of x is 2400x minus 2x squared. So I'm just going to write that down here so we have it. A of x is equal to 2400x minus x squared. So we could consult Desmos or just do a brief sketch of this function on our own. So we see here that at 600, we have a max. We can see that at 0, so a of 0, our output is equal to 0. So our function's down here. So that means that our function looks something like this: increases until 600 and then decreases. And that is area of X. And the output is going to be in square feet, because we're using feet in all our dimensions. Okay, so are we done with this problem? Well, let's look back at what the question asked us. The question in this statement, or in this problem, is what are the dimensions of the field that has the largest area? What did we find? We found that when X is 600, the area is optimized. Is 600 the dimensions? No, 600 is only the dimensions of this side of the fence. We don't know, or we haven't computed what Y is yet. So how do we compute Y? Well, we have a constraint that gives a relationship between X and Y. That's written here as well. So we can use that constraint to find Y. I'm going to say use the constraint 2400 equals 2x plus y to find y. So we know that x is 600. So that gives us 2400 equals 2 times 600 plus y. So that gives us 2400 equals 1200 plus y. So I can subtract 1200 from both sides, and I get that 1200 equals y. So now we can answer our question. So the dimensions, let's get it off of shape. The dimensions that maximize area are the X value needs to be 600 feet and the Y value needs to be 1200 feet. All right, now just for a little extra in this problem, what if instead of the dimensions that maximize area, they asked us for the maximal area? So we are so close to finding that value. We know that area is equal to the X times the Y. So the maximum area is going to be 600 times 1200. So if we compute that out, we consult our calculator, or maybe do it by hand. I'll cut to the chase here though, and we get 720,000 square feet. So that would be the maximum area, which is the area associated with these dimensions. Awesome work, everyone. So at this point, please pause the video and rewatch any parts of this preliminary example to start feeling more comfortable doing problems and calculations like this. Awesome. In the next video, we're going to go over those key steps in optimization problems.